Okay, so we're going to be looking at minimum cut and maximum flow. This is lesson 8 for our max flow lessons. Okay, objectives is we want to look at the cut capacity. Okay, again, we're looking at the max flow and we're going to relate this to the minimum cut. What we're going to find out is that these two things are in fact equal to each other. Okay, let's give this a go now. Right, so in relationship to the cuts, basically what we're trying to do is we're trying to separate the source from the sink. Okay, so for this example here is we've got the source, which is over here, right, and we've got the sink, which is over here. All right, so once again is we identify the source by all of the arrows pointing outwards from it, and we identify the sink as all of the arrows pointing inwards to it, like so. Okay, so source and sink. Now I could do a whole series of cuts in relationship to this diagram here. All right, so if I did some cuts, as an example, a dotted line here, let's call this cut A. All right, yes, it is separating the source from the sink. And what's happening is I'm going to cut through this line, right, this line, and this line. So these three lines I'm cutting through. So if I add those three together, I've got 1,000 plus 400 plus 600. So the value of this cut is equal to 2,000. All right. Now, what we're going to try and find here, if I went through this activity and what I would try and do is I went through and did its max flow. Okay, so if I went through and did the max flow for this question here, is I would have SBA, which would be equal to 700. So cross it off, put a 0, cross it off, put 300. I would then have SCA, okay, which is going to be equal to 400. So cross it off and put 1100 like so. So I would have 400 along that path. I would then have SMA, all right, as my last one there, which is going to be equal to 600. So adding this all up, my max flow, as we've done before, is going to be equal to the addition of these. Okay, so just finishing that off there. All right, is we end up with 1,700. Okay, so my maximum flow is equal to 1,700. So what I want to try and do is I want to try and create a cut through this here to equal to the maximum flow. All right, so what we do is we create this rule, which is the min cut is equal to the max flow. All right, so if we can actually establish where the minimum cut is, it is actually equal to the maximum flow. So I'm just going to get rid of some of my numbers that I've done before. All right, I don't need those just anymore. I've got those written on the side. If I create some more cuts, so for example, this one here, I've separated the source from the sink. So for this one, I've got 700 plus 1,500 plus 1,200. Okay, 7, that's going to be equal to 3,400. So it's obviously not that one. All right, let's try another one. What about if I did one like this? So down here, through here, and then down like so. I've got 700 plus 1,500 is 2,200, 2,800, and 3,400. Again, that's no good. I want it to be 1,700. Let's try another one. Here, down here, through here, and through here. I've got 700 plus 400 is 1,100 plus 600 is 1,700. There we go. I found my minimum cut because it's lining up to that. Okay, so there's my minimum cut, which was that cut I did at the last. That's purely what we're doing with this exercise here. Okay. All right, let's just erase this so I can see what we have written. Okay, imaginally breaks through the network, okay, to separate the source from the sink. There are a few special cuts that we'll see a little bit later on and how these apply. Okay. Now, we've already spoken about this, is the first one would in fact be a valid cut because it's separating the source from the sink. The second one would not be a valid cut because it is not separating the source from the sink here. Okay, so I can still go this way in order to get to the sink, so it is not a valid cut. Okay, and the last point, most important, cuts can only pass through each of the edges at most once. All right, so we've just looked through this one. Cut capacity of C1, 3,400 as we did before. Cut 2, add them up, 2,000 as we did before. Cut 3, it's going to be equal to 3,400. Alright, and we're going to get to this special example here where we're not going to actually count one of these. Okay, we'll talk about this one in a second. So as we continue through, cut 4, like so. So, what's happening with this one? We want to ensure with our cuts, I like to do this. So with my cut, which I've got here in yellow, all right, if I loop that back around, okay, to the source effectively, so back over here to a source. What I want to ensure is that with each of the lines I pass through is I go from the source, okay, so inside this area which I've created, they go from the source to the sink, okay? So the cuts which go from the source to the sink are the 1000, the 400, and the 1200, all right? So I'm going to be counting those ones, all right? Now, one of these ones, the 600 here, we can see that one actually goes from the sink back to the source, all right? This is going to create an issue. Okay, so what's happening as written here is it's actually carrying material from the sink back to the source. All right, so in relationship to this, okay, so for the cut for C4, we are not going to count something which is doing that. So for this cut here, we are only going to count the 1000, right, the 400 and the 1200. We are not going to count the 600 because it's returning flow back into the source. Okay, so in my circle or my shape which I've created to out, so the arrows need to go from in to out, they don't go from out back to in. All right. Okay, so multiple cuts here. Calculate the cut capacity of the 4 cuts shown in the network on the right. The source is the vertex S as shown, and the sink is vertex T. All right, so for cut 1, right, simply going through adding the 2 together, 35, pretty self-explanatory. Cut 2, all right, you've got 20, and you probably need to be careful because F to B is actually going from outside, so it starts outside here and then it goes back into the source. So remember, if we loop that back around like so, it goes from out to in, so we're not going to count that 6. All right, so don't count the 6 in your cut there, so 34. All right, as we've just suggested there. Cut 3 is going through, pretty easy addition there. And cut 4, once again, is that we can see something going from outside the cut to inside, which is that number 12 once again. Okay, so we don't count it. So 20 plus 10 is equal to 30. All right. So from our last assessment, we can calculate the value of the several cuts shown. We have one of them here, 35, getting practice at this. Here is another one. Okay, once again, we're not counting this value here of 9 because it goes from out to in. All right, 44. Okay, again, not counting A and B. We have that cut there, which is going to be equal to 34. All right. And there is a theorem that what we just said before, that the maximum flow is going to be equal to the minimum cut, as we suggested with our first example in this video. The alternate path or the alternate way is the exhaustion of paths, which is going to be doing the lists of S, C, T, as we just did in the previous video. Okay, and writing how many you can fit across there, which is obviously 10, going through the other ones, etc., etc. Okay. So we used that algorithm last time. All right, if a cut is drawn only through the edges that have a residual capacity of 0, then the original cut capacity of these edges will be equal to the maximum flow. All right, so basically what this means is you want to try and use the zeros in some way, okay? And what you'll find is that that will in fact be pretty closely equal to your minimum cut, okay? So for our minimum cut here is we've got 10, we're using a 0, the 9, we're using the 0, this one here, we're using a 0, and down here, we are in fact using a 0, all right? There is also that 0 here, Okay, and as you can see, it probably doesn't matter because you've got 18 and you've got to go through 9 and 9 anyway. Okay, so that's still adding up to the 18, which is why this is kind of a bit of a special circumstance where there may in fact be 2. Okay, so you could either do either one for that one. As suggested, there's 2 possible cuts drawn here. All right, so looking for the zeros. Either way is simply just looking for the smallest numbers, trying to go through the smallest number. So across the top, you've got 10 and 12, which go to the same space. Obviously, you're going to select the 10, okay, obviously. Here you've got 9 and 18. In this case, it doesn't matter, because if you go through this 9 as suggested before, you've got to go through this 9 to get over to there, okay? All right, perfect. All right, and there's the other one in green, which again still produces the same number as we just said before, following through the zeros. Okay. Right, guess and check, or you can look through a systematic approach, okay, which is going to be looking through the smallest numbers. Again, as I suggested, if you've got 700 and 1,000 to get into this first space here, I know to create a minimum cut is I probably want to choose the smaller of the 2, being 700, which is why I'm going to cut through this part first. All right, so then be kind of clever. Well, you've got 1,200 and 600. It's probably pretty likely you're going to go through the 600. Okay, all right, and then you've got the 400 here as well. Again, there's a bit of a system, obviously, involving for that. Okay, and we did that question at the very start of this video. Show the minimum cut that corresponds to the max flow from S to T. Use systematic working exhaustion from here, okay, to verify your solution. All right, so to verify some of your cuts, you may in fact choose to do something like this. All right, here's one cut, 8 plus 11. So cut 1. There's another cut over there on the side, cut 2. Here's another example of a cut here, cut 3, cut 4. Okay, I think that's about all of them. All right, so we've got our cuts there, 19, 9, and 7. All right, so max flow equals to minimum cut. So our minimum cut there, all right, is going to be the 7. So therefore our maximum flow through this network is going to be 7 units. If you went through and did this, okay, you would also find that is in fact the case. So working through that path there is 3, cross the numbers off. Here is our next one. Through that path is 3, cross the numbers off. And then working through the bottom there, right, is we end up with 1, add them together, we end up with our maximum flow of 7, which supports our minimum cut from before. Okay, looking for your zeros, okay, as you did before. All right, so what we had before, through the zeros, that one doesn't count because it's going back in, and there's our 0 there. Okay, so there is my cut. So looking for the zeros, and again, that does not count because it's going from outside closer to the sink back into the source, so it does not count. All right, and as we suggested, the minimum cut was also equal to 7. Perfect. Okay, very good.